Hi, everyone. In this lesson, we're going to finish up chapter 1, and we'll continue where we left off from the last lesson, which is at example 3. Example 3 and example 4 are two more examples where we're going to cover the difference between a parameter versus a statistic, and then we'll get into some new definitions. We'll do a couple more examples, and then we'll wrap up chapter 1. So example 3 says, a research medical team using data from a sample of 5,000 sport-related injuries reported that the average recovery time for a broken ankle is 7 weeks. Is this average an example of a parameter or a statistic? So let's quickly review the difference between a parameter and a statistic. So remember, a parameter is a number that describes a characteristic of a population, and a statistic is a number that describes the characteristic of a sample. So in this case, the question is this average, the average recovery time for a broken ankle, is that a parameter or a statistic? Now, this average recovery time for a broken ankle is based on a sample of 5,000 sport-related injuries. So since this average is describing the average of a sample, this is considered a statistic. Example 4 says, suppose the heights of all NBA basketball players were recorded and the average height is 6'7". Is this value an example of a parameter or statistic? So we're being asked about the average height. Now, you have to ask yourself, are we looking at a population of basketball players, or are we looking at a sample of basketball players? This particular example, we're looking at the heights of all NBA basketball players. So all implies that it's the entire population. So since this average height of 6'7" is describing the average of the population of NBA basketball players, we're going to consider that average a parameter. So hopefully these two examples, example 3 and 4, and then the previous examples 1 and 2 from the previous lesson really help illustrate the difference and help you to understand the difference between a parameter versus a statistic. So moving on, let's cover descriptive statistics and inferential statistics. Now, in that introductory video that you guys watched before my first lesson, you were told about descriptive statistics and inferential statistics. So in that video, you were given examples of descriptive versus inferential statistics. So I think of the word describe whenever I think of descriptive statistics. So descriptive statistics can include numerical and/or visual techniques, such as graphs, tables, to summarize data in a clear and effective manner. So basically, we're describing our data, and there's different ways to describe data. We could do it numerically and/or visually. The branch of inferential statistics is the process of using the sample information that we have to draw inferences or conclusions about the population. So think infer means to conclude. So whenever we're using the process of collecting sample information, and then we're going to draw inferences about the population from which we sampled, that branch is called inferential statistics. If we're just going to collect data and organize it and, use numerical and/or visual techniques to summarize it, that's an example of descriptive statistics. So those are really the two main branches of statistics. We're going to start this semester. The first couple of chapters are going to illustrate descriptive statistics. The second half of the class, we're going to move into the inferential statistics. So let's look at example 5. Really the next examples, 5 through 8, we're going to ask ourselves whether the scenario is describing descriptive or inferential statistics. So let's look at example 5. So it says a meteorologist constructs a graph showing the total precipitation in Phoenix, Arizona in each of the months of 1998. Does this involve descriptive or inferential statistics? So we have this meteorologist, and he or she is constructing a graph that's going to illustrate or show or visualize or describe the total precipitation in Phoenix, Arizona in each of the months of 1998. This is an example of descriptive statistics. Since the only thing going on here is just using a graph to describe or show our data, there's no conclusions being made about the population. So let's look at example 6. Example 6 says 30 of the 198 students enrolled in Statistics 101 were asked if they wanted exam 2 to be a take-home or an in-class assessment. 20, or about 67% of the students polled, indicated a preference for an in-class exam. The professor concluded that the majority of students in Statistics 101 would prefer an in-class examination for the second assessment. Did the professor perform a descriptive study or an inferential study? So let's kind of go back to the beginning. So it says 30 of the 198 students were asked if they wanted exam 2 to be take home or not. So that 30 is considered a sample. So of that sample, 67% said that they would prefer an in-class exam. Now, if we were to just stop the question there, this would be an example of descriptive statistics, because that 67% is just describing the percent of the sample that would prefer an in-class exam. But the question goes on to say the professor concluded that a majority, and I'm going to highlight this word concluded, that the majority of the students in Stat 101 would prefer an in-class exam for the second assessment. So the fact that the professor used the information that he or she got from the sample to draw a conclusion about the population, that's an example of an inferential study or inferential statistics, because we're using the sample information to draw a conclusion about the population. And that's the definition, if we look above, of inferential statistics. It's the process of using sample information to draw conclusions about the population. So this is going to be an inferential study. Example 7. A survey of high school teenagers reported that 79% of those sampled are interested in pursuing a college education. Does this statement describe descriptive or inferential statistics? So this would be an example of descriptive statistics, because that 79% is just describing a survey, which, remember, a survey is a sample. So it's just saying, okay, 79% of this sample of high school teenagers said that they want to pursue a college education. There's no inference or conclusion being made about high school teenagers, as a whole, as a population. So since there's no inferences or conclusions being made about the population, this is not an example of inferential statistics. That 79% is just describing a characteristic of that survey. So this is going to be an example of descriptive statistics. So let's do one more example just to make sure we're clear between the two branches. Example 8 says, parking at a large university has become a very big problem. University administrators are interested in determining the average parking time, the time it takes a student to find a parking spot, of its students. An administrator inconspicuously followed 250 students and carefully recorded their parking times. The university is interested in using the information from the sample of 250 students collected to learn information about the entire student parking population. Would this be an application of descriptive or inferential statistics? So this example would be an application of inferential statistics. And the reason is because an administrator inconspicuously followed a sample of 250 students and carefully recorded their parking times. Now, the university is interested in taking that information from the sample and learning more information about the entire student parking population. So remember, whenever we use the information from a sample to draw conclusions about the population, that's an example or an application of inferential statistics, which is what we have here. All right, so let's move on to section 1.2, which talks about why do we sample? And I started talking about this in the last video. So remember, sampling is the process of selecting a portion or a sample of the entire population. And I had stated earlier, a survey, well, actually, no, I talked about what a survey was. So I said, think of a survey as a sampling. So a lot of times we think, okay, when we survey a group, right, it's asking them a set of questions. So a survey comes in different forms, but if we were going to survey every item or individual of the population, we call that a census. And you guys might have heard of the word census before. Now, a census, a lot of times, is impossible because remember, a census would include every item or individual of the population. Now, why is it impossible? So that kind of brings us to the question, why do we sample? And the reason is, so samples are taken when it's either impossible or impractical to examine the entire population. I think one of the biggest reasons is realistically is that when the population is extremely large, it's very impractical, right? It's going to be very difficult to collect information on every item or individual in a population. But there's more reasons for sampling. So if we look at reasons for sampling, a census is impossible, right? So that would be collecting information on the entire population, especially larger populations, not realistic. Two, it's costly. It costs money to conduct these surveys. So a lot of times it's impractical to examine an entire population because it costs too much money. Reason three is that it's timely. It also takes a lot of time. And reason four is accuracy. So the larger the population, a lot of times the more inaccurate, our results or information tend to be. Now, when we sample, we always want to make sure we take a representative sample. Now, a representative sample has all the pertinent characteristics of the population in the same proportion as they are included in that population. So what that means is when we sample from a population, we want it to be not biased. So we want it to have those characteristics that are pertinent in the actual population. And we're going to do an example or a few examples where we have to decide if we have a representative sample. So we'll look in a minute. Before we get to the next set of examples, let's just cover section 1.3, which is sampling techniques. Now, in statistics, realistically, there's a lot of different ways that we could take a sample. In this course, for the most part, we're always going to assume that we're taking a simple random sample. Now, a simple random sample is kind of what it sounds like. It's going to be a sample of data values that we select from a population in such a way that every sample of size n has an equal probability of being selected. And every data value of the population has the same chance of being selected for the sample. So completely random. And every item or individual has the same chances of being selected. Selecting a non-representative or a biased sample from a population can lead to invalid inferences or conclusions about the population. So we always want our sample to be representative or not biased. So let's make sure we understand these terms. And I think the best way to do that is let's look at a couple more examples. So let's look at example 9. So example 9 says an NCC professor decides to conduct an opinion poll of students attending NCC during the fall semester. Upon using a random number table, she selects 200 students enrolled in day classes. Does this sample represent a random sample of all NCC students? So you're probably thinking, no, it's not representative, right? It's not representative of all NCC students. So remember, we said that a sample, representative sample, has to have all the pertinent characteristics of the population in the same proportion that as they are included in that population. So let's think realistically. If you're a student at NCC, maybe you take day classes, maybe you're a nighttime student, maybe you're an online student, maybe you take classes on the weekend, right? those are all the different characteristics, or not all of them, but different characteristics, right, that a student may possess in the true population. But if we're only going to select 200 students that are enrolled in day classes, none of the other students, the night students, the weekend students, the online students, they didn't even have the opportunity to be in the sample. So this sample is not going to represent all NCC students. This is only going to represent the day students, right? So this answer is no for that reason. So let's look at example 10. The population is all females between the ages of 17 and 35 living in New York State. The sampling procedure is devised to select a sample of 100 female college students within New York State. Does this sample represent a random sample of all females between the ages of 17 and 35 in New York? So remember, if we're going to take a sample, it has to have, all the different characteristics of, the population in the proportion that they're included in the population. Now think of females between the ages of 17 and 35. Not every 17 to 35-year-old goes to college, is a college student, right? So we're only selecting 100 female college students. They might not necessarily, right? So even though they might be between the ages of 17 and 35, not every person in that age range, right, goes to college. So this sample is not going to be a representative sample of all females between the ages of 17 and 35 because not all of them necessarily go to college. So the answer to that is no. Example 11, the population is defined to be all the people who shop at the Green Acres Mall during the week before Christmas. The sampling procedure is devised to select every 25th shopper who enters the mall at only one of its 10 entrances. Does this sample represent a random sample of all the people who shop in Green Acres Mall during the week before Christmas? So the issue with this is that there's 10 entrances. But this procedure is only going to select every 25th shopper who enters the mall at only one of the 10 entrances. So it's only focusing on that one entrance. But what about all the other people that go in through one of the other 9 entrances, right? They would never have a chance to be in the survey. So this sample doesn't represent a representative random sample of all the people who shop at the Green Acres Mall, because it's not inclusive of the people that use the other entrances, right? Maybe somebody lives closer to one entrance and every time they go to the mall, that's the entrance that they use, right? So this would not be a representative random sample of all the people who shop at the Green Acres Mall. And let's do one more example. Example 12 says the population is all the faculty members teaching at the Nassau Community College. The sampling procedure will select a sample of 25 faculty members using the following procedure. The name of each faculty member is placed in a large drum. The drum is rotated several times before each of the 25 names are selected. Does this sample represent a random sample of all NCC faculty? So in this case, it does, because every single faculty member's name was placed in this drum. It was mixed up and 25 were randomly selected. So every faculty member had an equal chance of being selected, and all faculty members were included in the process. So even though one of them might not necessarily have been picked, there was a chance that they could have been. So everybody, potentially had the same chances of being selected in this random sample. So the last 2 sections in chapter 1 covers the uses of statistics and the misuses of statistics. So you'll see throughout the semester, the many different uses of statistics, But really, this is kind of, a brief summary of how statistics are used, in many real world different fields. And I listed a few: economics, finance, psychology, sociology, education, physical sciences. So that's just to name a few. Extensive data collection and distribution activities are performed by the federal and other governmental and private agencies in areas such as education, employment, health, crime, prices, housing, medical care, manufacturing, agriculture, construction, transportation, etc. So there's all different fields that require, extensive data collection in order to analyze, different concepts or areas. And the development of the computer has led to a revolution in the area of data collection and analysis. So statistical analysis can now be applied to vast amounts of data accurately and quickly. And some areas where you guys are familiar would be weather forecasting, right? So, on your phone, if you open the weather app, right, it'll say, okay, there's a 10% chance that it's going to rain today, right? That's probability and statistics. Another example would be economic stabilization, disease control. So these are, different problems that are being solved using statistical analysis. And when we move throughout the semester, we're going to be doing all different types of examples where we can use statistics. But at the same time, you also have to kind of keep in the back of your head that people can misuse statistics as well. It's very easy to present information or data in a misleading way. And I gave 4 examples here. Number 1, misleading graphs, and we'll look at an example of a misleading graph. We kind of just talked about, taking a non-representative sample, right? It's going to be biased. It's not going to represent the population accurately. 3, inappropriate comparisons. So a lot of times people will make comparisons, but they're inappropriate, and it's going to lead to conclusions that might not necessarily be accurate. And then 4, the omission of variation about an average. So if we omit certain information, right, that could be very misleading. And when you're reading chapter 5, and you'll also be assigned some homework questions, we'll be able to further, give examples as to how statistics can be misused. But I have one example here, and this is going to be the last example on this chapter 1 worksheet. So this is an example of a misleading graph. So it says an investment analyst could use a graph to show that the rate of return on retirement annuities are falling. However, if the analyst wanted to make the decrease in the rate of return appear more dramatic, she could simply change the units of the vertical scale and delete its lower portion. So we'll look at these in a minute, and I'll blow these up a little bit. But it says, although both graphs present the same information, the graph on the right presents the distorted impression that the rate of return is dropping at an incredible rate, right? So if we look at this, the one on the left, if we look at the vertical scale in terms of interest rates, it starts at 0, goes to 2%, 4%, 6, 8, 10, 12, and so on and so forth. So when the information was plotted on this graph month by month, it looks like a very gradual, right, decrease in the return rate. But look at the difference on the graph on the right. Months is still the same for the horizontal axis, but look at the vertical axis. Instead of counting by 2s, the graph starts at 9.5%, and then it goes in 0.2s, right, up to 9.7, 9.9, 10.1. So there's a much smaller gap between the numbers right on the scale. So when these same points are plotted, it's going to look way more dramatic, right? So like if we look at this first point over here for January, it's about 12%. This is the same point right here on the graph on the right. Now look at February. February still is about 12%, right? But now if we look at the graph on the right for February, now that the scale is more precise, right, there's more detail, we could see it's, about 11.8%, and so on and so forth. So by changing the scale, we could see now this dramatic decrease in the rate of return. when it really wasn't that dramatic, right? We're going from about 12 to 11.8. It looks like March is about 11.7, right? Not that much of a decrease overall. But when you make these numbers, right, not in terms of jumping in twos, let's say, like the graph on the left, it's going to make this decrease seem way more dramatic. So this is just a nice example of how, a set of graphs or a graph can be misleading, just all by, changing a scale or vertical axis in this case. So this pretty much wraps up chapter 1. The next lesson, we're going to start chapter 2.